miss seeing you because I'm doing this before class, so you get a sneak peek. Today, we're going to go over, in this video, we're going to go over 5.3. And there's one other piece of information that I want you to have. So have your 5.3 notes in your theorem sheet. And then I'm going to send this file out that's called centers of triangles. So we're going to talk about this too. So remember, we started talking about centers of triangles on, what day was that? Monday. And so we're going to keep talking about ways to find centers of triangles. So that's what we're going to do today. So I'm going to go ahead and share my my notes so that we can kind of talk through centers of triangles. So here we go. Hopefully this works out. All right. So what I want to start with is that sheet. So I have I don't know, you techie people can figure it out. There's probably a better way to do this. But as I mentioned on Monday, there's more than one way to find the center of a triangle. So surprise, here's a nice little chart to help keep us organized and figure out the center of the triangles. But what I wanted to start out with is we already discussed the circumcenter on Monday. So I just want to make sure that we get this filled in, and it's a good review before we start in the new section. So if you recall, on Monday, what we learned about was finding the perpendicular bisector and using the perpendicular bisector to find the circumcenter of a triangle. So when we're finding the circumcenter, that is created by using the perpendicular, created by using the perpendicular bisectors, right? So this shouldn't be any new information. Bisectors right here. We use the perpendicular bisectors to find the circumcenter. So in this triangle up here, if you want to know what the perpendicular bisectors are, they are these three segments here. I know they're perpendicular bisectors because they're at the midpoint. I know they're at the midpoint because they're equidistant away from each endpoint, and they're at 90 degrees. So these three red lines are my perpendicular bisectors. And then remember, once you find that point of concurrency for those three perpendicular bisectors, which is M, if you then draw a line from that point of concurrency to the vertices, right? Oh, we're going Christmas here. That means that all three of those lines, AM, BM, and CM, are all congruent to each other. They're all equidistant away from each other. So the important fact is that the circumcenter, is equidistant from each vertex of the triangle. So that's what the green lines show, right? The circumcenter here at M is equidistant from each end point, each vertex, right? A, B, and C are your vertex, and they're equidistant from each other. So that's the important fact for the circumcenter. The other thing that I would like you to add on here that's just going to help you out a little bit is that we're going to kind of rewrite this word. That means that, well, we'll keep it in green because it's the same thing. That means that A to M is equal to B to M is equal to C to M, right? That's just the same fancy way of saying that the circumcenter is equidistant from each vertex. And then the last thing that I think is helpful to add on to your chart is that we know how to find the circumcenter thanks to theorem 5.4. And that is, and I don't have room, I'm running out of room here, but that's the concurrency of perpendicular bisectors of a triangle. So theorem 5.4 is what covers how we find the circumcenter of a triangle. Okay. Again, this is created by using perpendicular bisectors. So that's a little bit of a review, and this is going to be something that you definitely want to print out and keep updated because you can also use that as a resource for your quiz and your test. Okay, so that's a little bit of review. Now we're going to start into 5.3. 5.3 is going to feel very familiar. So in 5.3, what we're going to talk about is we're going to talk about angle bisectors. So, I'm getting fancy with my colors here. All right, so we're going to go to 5.3. And we're going to be talking about angle bisectors. So we actually already have a definition of what an angle bisector is. right? An angle bisector is it's generally a ray, but it could be a line, a ray that divides an angle into two congruent parts. So let's say I have an angle, right? Here's my, whoa, my angle, and I divide it into two equal parts, right? This blue ray would be my angle bisector, because as long as these two angles are congruent. So it divides it into two equal parts. So we'll go ahead and call this A, B, C. So, and D. So if I was using geometry terminology, I would say that ray AD is the angle bisector of angle BAC, because it divides angle BAC into two equal parts. So that's actually not any new information. The new information that we are going to learn with angle bisectors has to do with a point on our angle bisector. So kind of like before, we had a perpendicular bisector, and we said, what happens if we pick a point on a perpendicular bisector? How does that relate? It's kind of the same idea for an angle bisector. So what this is it's a theorem. Surprise, right? And it's down here. This is what I'm going to talk about right now is called theorem 5.5, which is the angle bisector theorem. Surprising, right? The angle bisector theorem. So let me read it off to you, and then I'm going to show you in this picture. The angle bisector theorem says, if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. Okay, so what this means is if you pick any point on your angle bisector, right, then that point is equidistant from the two sides of your angle. All right, so that means that if I draw a line from here to one side of my angle and a line from here to the other side of my angle, these two are equidistant away and therefore congruent to each other. All right, so if I pick any point and I draw a line, then they're equidistant. So this should feel pretty familiar. It's just like perpendicular bisector, right? The trick with this is that when we say that when you draw a line from a point on the angle bisector to one of the sides, when they say that when you draw that side, you'll see in there it says that distance means the shortest length between two objects. The shortest length between two objects. So how do you know? Because let me give you the opposite scenario here. Okay, let's say I pick this point on my angle bisector and I draw a line to side AC, but then I draw this line to side AB like this. Do those two lines look equidistant? No, they don't look equidistant. So we have to have some way to know how to draw those lines. So you're drawing the line that is the shortest distance away. And when you draw the line that's the shortest distance away, that happens to always be perpendicular to the side, which is pretty cool. So if you want to find the shortest distance from an angle bisector to the side of an angle, it's always going to be the line that's at 90 degrees to the side. And so as long as we follow that rule, then it's super easy to figure out those two lines that are equidistant away from a point. All right, so then again, this doesn't have to be that particular point. I could pick this point out here, right? That is on my angle bisector. As long as I draw the line that's the shortest distance, which means it's going to be the line that's at 90 degrees, and I draw this line at 90 degrees, then these two lines that I have formed are equidistant and therefore congruent to each other. So that's what the angle bisector theorem says, which you can see right here. It says, if a point is on the bisector, so point D is on the bisector of an angle, then it is equidistant from the two sides of the angle. And you see over here, in geometry, distance means the shortest length. So that's how we know that it has to be at 90 degrees, so it's the shortest length. So if you want to use that in geometry, language, you would say ray AD bisects angle BAC. And DB is perpendicular to AB. So DB is perpendicular to AB. and DC is perpendicular to AC. So that's this little extra part where you know that the line you draw has to be at 90 degrees. Then we know that DB has to be equal to DC. Okay, so pretty straightforward, what we've already talked about before. And then you'll notice while I'm down here, we also have the converse of the angle bisector theorem. So converse means switch the hypothesis and conclusion, right? And so that's the same idea. In angle bisector, we had an angle bisector, so then we know that the distance from the angle bisector to the two sides is equidistant. If we do the converse, then if we know that the distance from the two sides to a point on the angle bisector is equal, then we know it lies on the angle bisector. Okay, so that's what this says more eloquently than I just did. It says if a point is on the interior of an angle and is equidistant from the sides, then it lies on the angle bisector, or the bisector of the angle. We don't even need that in there. Bisector of an angle. Okay, so if DB is perpendicular to AB and DC is perpendicular to AC and DB is equal to DC, then ray AD bisects BAC. So kind of the reverse, if we go back up here, if I don't know if it's the angle bisector or not, but I gave you this picture. So I don't even know if AD is the angle bisector, but I gave you this picture and I said, hey, guess what? I'm not right on my points here, but you guys will get the idea. DB is perpendicular to AB and DC is perpendicular to AC and BD is equal to CD, then I could tell you for sure that AD is a perpendicular bisector. So it's the opposite of that. Okay, so let's do a couple of examples of this just to make sure that everyone's understanding. So this is called use the angle bisector theorem. So in this picture right here, this is example number 1, and it says find the measure of CBE. Okay, well, let's look what's going on in this picture. CBE is an angle. We've also have angle CBD, right? And you'll notice what's going on here is that there's these two distances here, and they're both 21. And they're equal to each other. They're also at 90 degrees to the outer angle. So because of this, if I use the converse of the angle bisector theorem, I can say that, oh, that means that BE has to be an angle bisector because these two sides meet all the criteria, right? And if BE is an angle bisector, that means it divides CBD into two equal parts. So if one part is 31 degrees, right? If EBD is 31 degrees, that means that CBE would also have to be 31 degrees. Okay, so it looks complicated, but not too bad. All right, next one. A spider's position on its web relative to an approaching fly. So here's your fly down here, and here's your spider in the middle. A spider's position on its web relative to the approaching fly and the opposite sides of the web forms congruent angles as shown. Will the spider have to move further to reach a fly toward the right edge or the left edge? Well, look at what's going on here, right? So this was what's going on here. This is a angle, and it appears to be an angle that has an angle bisector, right? So the fly is traveling a straight line basically right now down the angle bisector of this. And I know it's an angle bisector, but angles in here are congruent. I know it's really small, so sorry about that. But LA spider is congruent to spider, LF spider is congruent to spider FR. And you can see that there's little hash marks in there. So if you look at what's going on in this picture, and we would actually draw from the spider to each side, we know it's an angle bisector, then will it have to move further to the left or the right? And the answer is it'll be the same distance if it moves to the left or the right, because that spider is going to have to move in equidistant to get to either side if it moves left or right. Hopefully I explained that pretty well. That's pretty intuitive, right? Okay, and then one more. this one's a little bit different. So it says, for what value of x, so we've got it, let me take a step back here. We've got angle KJL, okay, and then we have some point P out here, and then we've connected KP and LP to that. So it says, for what value of x does P lie on the bisector of J, of angle J? Okay, so if we want JP to be an angle bisector, what has to be true about these two segments? Well, what has to be true is they have to be at 90 degrees, which it doesn't really tell us, but we're gonna assume that they are just for this example. And then that also means that KP and LP have to be equal to each other. So if you want to find a value of x so that P can be on that angle bisector, that means that these two segments have to be congruent. So KP would have to equal LP, which means that x plus 1 would have to equal 2x minus 5. Okay, and then if we do some solving, we get x minus 5. X would have to equal 6 in order for this to work, for JP to be on the angle bisector. All right, so I think that's pretty straightforward, especially in light of what we learned about perpendicular bisector. Now, but wait, there's more. Did you miss that in class? All right, so there's one more thing that I want to share with you, and that is, hey, we just talked about perpendicular bisectors, and we can use perpendicular bisectors to find the center of a triangle. Well, another method to find the center of a triangle is by using angle bisectors. Okay, so last night I was thinking about this and I was trying to think of a good example, and my example is not that great, but at least it'll be funny. Okay, so we've got a triangular shaped yard. Okay, yeah, we'll do this. We've got a triangular shaped yard, and let's imagine that this triangular shaped yard is surrounded by an electric fence. Okay, so it's an electric fence that's going to keep the puppy inside your yard, right? It's a cute little puppy. And the puppy has figured out that if it can stand the same distance away from all three sides of your electric fence, that it reaches this place of, perfect synergy, and it forgets about all of the electric fence. So basically your puppy, your cute little puppy, gotta try to draw a puppy, right? Your cute little puppy wants to stand somewhere inside the triangle, and he doesn't want to be equidistant away from each vertice. He wants to be equidistant away from each side. So that way he's the furthest away he can be from the electric fence. Okay, so that's what we're going to talk about today, is how can we find the point that is equidistant from all three sides? All right, for example, if I drew my cute puppy here, right? He's this far away from the fence here, he's this far away here, and this far away here. It's not a bad guess. Like, those look pretty good, right? But if my puppy stood, sorry, puppy, if my puppy stood over here, he's going to be this far away from this fence, that far from this fence, and this far from that fence. So he's not going to be, he's going to be a lot further from the fence line over in BC. So he wants to figure out where he can stand, where he's going to be equidistant away from the fence, so the least likely to get zapped by the poor electric fence, right? So in case in your head you guessed it, in order to find the center of the triangle that's defined as the place that is equidistant from all the sides, we are going to use angle bisectors. In case anyone didn't guess that, because we just were talking about angle bisectors, right? So this method is called finding the in-center. So remember yesterday, using perpendicular bisectors, we found the circumcenter. Today we're going to use the in-center. Okay, so to find the in-center, what we're going to do is we're going to use angle bisectors instead of perpendicular bisectors. All right, so to use angle bisector, what we have to do is we have to bisect all the angles. So the first thing we're going to do is go down to angle BAC, or angle A down here, and we're going to draw the angle bisector. right? And this is just me eyeballing it, right? So when we draw the angle bisector, remember it creates two congruent angles within there. So that's what we're going for with angle bisector, right? And when I draw the angle bisector of B, then we've got two congruent angles here, right? And when I draw the angle bisector of C, then I get two congruent angles down here. Okay, then all three of those, right? All three of those match up at a point that we are going to call the in-center. So this is the in-center. At that point right there. Now, that's the in-center. Are we done? No, not quite yet. This is where our puppy's going to stand, right? So cute little puppy. He's got to stand right here, right at the in-center. When the puppy is at the in-center, right? If you then draw a line from the in-center to the shortest distance on the side, remember the shortest distance on your side is the one that's at 90 degrees. Okay, so I'm going to draw from the puppy to line AB. That's what I just did. From the puppy to line AC, again, has to be at 90 degrees. And from the puppy to line AC down here. I think I might have said the wrong word before, but okay, there we go. So when you just draw these lines from the in-center to the sides, remember they're at the shortest distance, which means at 90 degrees. Okay, got a lot of brown and red going on. So when you find the in-center, you're not finding the spot on the triangle. You're finding the spot on the triangle that is equidistant from all the sides, not equidistant from the vertices like the last time. So in this case, when we found the in-center, that means that we'll call the center P for puppy. That means that from, oh, I need some more letters. D, E, and F. From D to puppy equals from E to puppy equals from F to puppy. Okay, so that's the in-center. And of course, we have a theorem for that. That's theorem 5.7. It's called the concurrency of angle bisectors of a triangle. So that's what we just talked about, right? The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So if AP, BP, and CP are the angle bisectors, so again, let me do a little highlighting. The angle bisectors are going to be in red, right? Then once you find that center, then from P to D, P to E, and P to F are all equal. So it's equidistant from the sides. So while we're here, let's go ahead and fill in your centers of triangle sheet too. So you can see that the in-center down here, right? The in-center is created by angle bisectors. So the circumcenter is by perpendicular bisectors. The in-center is by angle bisectors. And it says that the in-center is equidistant from each side of the triangle. So circumcenter and in-center are kind of the same in that they're talking about the distance from the sides versus vertices. That's the difference between the two. Okay, so in this picture, the A to M, B to M, A to M, B to M, and C to M, those are your perpendicular bisectors. Right, those are your perpendicular bisectors. And then the sides that are the same are Y to M, the distances that are same. Y to M equals X to M equals Z to M. Sorry, that's out of alphabetical order. And then again, we just learned that this is from theorem 5.7. Okay, one last thing that I want to tell you about this, actually two things. One of the cool things about the in-center that's different from the circumcenter is that the in-center is always inside the triangle. So I don't know if you remember on Monday what I said, the circumcenter can be outside of the triangle. The in-center is always on the inside of the triangle, no matter how you do it. So you cannot have an in-center that's somewhere off triangle. The other thing that's kind of interesting is, and they have this relationship with each other, right? Circumcenter, if you remember on Monday with a circumcenter, just trying to decide what color I want here. When you did the circumcenter, I said there's one other cool thing, right? It's circumscribed in a circle, right? Point, oh wow, that's a lovely circle. But if you just keep drawing, it gets better, right? Point M is in the center of that circle that's met when you hit all the vertices. Okay, when you talk about the in-center, it also has a relationship to a circle, but the in-center actually happens when you draw a circle inside the triangle. Okay, point M is the center of a circle that passes through points X, Y, and Z. So circumcenter is when you're connecting all the vertices, and then M is the center. And the in-center is when you're connecting these shortest distance from the centers, and you draw the circle on the inside. So I think that's kind of interesting. Okay, I'm going to do one more example. This one just could be possible help from your homework, because I want to show you what happens when you're finding the in-center, and you might have to use your friend Pythagorean theorem. So this is the last little example. If you want to come back to it once you're doing homework problems, if you have problems with that, you're welcome to do that. So in the diagram, L is the in-center of triangle FHJ. So they actually tell you that L is the in-center. All right. So then we would know that, for example, FL is an angle bisector, and HL is an angle bisector, and JL is a perpendicular bisector. Angle bisector, sorry. Find LK. So LK is, let me get it on my, LK is the distance from here to here down here. All right. So it says, by the concurrency of angle bisectors of a triangle theorem, the in-center L is equidistant from the sides. From the sides of FHJ. Actually, let me zoom in a little bit because this triangle is tiny. Maybe this will help me out. There we go. Okay, so we want to find LK, but we know from the theorem that if this is the in-center, that LK has to be equal to LI and LG. All of those are equal to each other, right? So if you notice up here, so from the theorem, we should know that LK has to equal LI, which has to equal LG, right? Because point L is the in-center, we know that, right? So all of those are equidistant from the sides. So to find LK, you can find another point. You can find LI in the triangle. The reason that they're focusing on LI is, look at this triangle here. LI has 2 of the 3 sides identified. So can we figure out the third side? Yeah, because it's a right triangle right there. You see how it has to be at 90 degrees in order to be the same distance from the in-center. So that's a little 90 or a little right triangle that we have hidden in our in-center. Okay, so if we can figure out what LI is, then we can figure out what LK is. And we can figure out what LI is because it's this little triangle in here that has a hypotenuse of 15 and a side of 12. And then this side over here is L to I, which we'll call X. Okay, so the Pythagorean theorem is C squared equals A squared plus B squared. Let's substitute what we know. We know the hypotenuse is 15 plus some side X plus 12 squared. Okay, if we simplify, we are going to get, we're going to get 81 equals X squared. Sorry for the quick math there. Or X equals 9. That's by taking the square root of both sides. Okay, X equals 9. So don't forget how to do that. So because LI equals LK, LK has to equal 9. So in these problems, you might have to pull out your Pythagorean theorem. So that's just a good review of that. All right, guys, I know that was a longer video, but hope that helped you. And I will put up a video later on 5.4. Take care. Bye.